Today, we're going to be talking about a paper from the Google DeepMind team, and I have Isaac with me here today, who's going to be presenting the paper.
Now, the practical part of the paper, they sort of implement two main experiments. I think these connect more directly to like real-world applications of retrieval, and so I'll dive into them now. It's easier to actually pull up the paper. Okay, so once we have this theoretical result, you're thinking like, can we get like a real-world experiment to validate this? But obviously, this experiment should be very ideal in the sense that we remove any sort of constraint on the embedding that isn't related to the fundamental like geometric like representation limits of the embedding. And so what the authors do is we start with n documents, like as we did before. And this time, instead of just having m be a random like free variable as a number of queries, we want n choose k queries. And so what this corresponds to is like n choose k is just like the number of size k subsets of n. And we want every query, when we do cosine similarity, we want the k largest values of like a query to correspond to what corresponds to a subset of size k of n. And we want every single n choose k queries to have a different top k, or aka like primarily retrieve a different size k subset of the n documents. And so as for why this is the sort of goal the authors are going for in this setup, it's to sort of see like, can we sort of like place these queries and vectors in such a way that like every group of k documents can be like sort of like the closest to a query. The analog of this is like in like a real-world application of information retrieval is like, can I have a vector embedding where if I phrase queries cleverly enough or precise enough that I can like retrieve any sort of combination of documents, and we are like fixing the like size of like the top k, just like otherwise it's like impractical to like even analyze. So I guess I'll write this out again, the main points. So n documents, and then n choose k queries. Each query goal is to retrieve a unique top k documents. And so this is the setup. We're just thinking like, oh, is this even possible? And how do the authors sort of like make sure that like if this experiment fails, it's purely because of like the limitations of vector embeddings and the geometry of all that. And how do they like sort of eliminate the chance that it's due to some like other non-optimal setup, whether it's like a loss function or like having like non-optimal like gradient updates, parameter updates. And without getting too into the weeds, basically they sort of use this approach called like free embeddings, where we remove all these concerns. And so some things they do is every single gradient update is a full pass. We're not doing like some sort of like batching, which could sort of lead to less optimal improvement or training. And so like every like the batch is like every epoch is one batch. They use this like InfoNCE loss function, which is the way it's defined. It's guaranteed to separate documents that you want designated as relevant and documents that you don't want designated relevant. And we know like the ground truth we want here because we can like assign every query to a specific size k subset, and these are the ground truth relevant ones, and then the other n minus k documents are the ground truth irrelevant ones. And if we set up the loss function so that like it knows what we're going for, it is guaranteed like mathematically to pull the similarity scores of the relevant ones higher and then the similarity scores of the irrelevant ones lower. So like basically the whole point is we've eliminated any other possibility within like the training hyperparameters or other setup where this sort of like training could fail for any reason that isn't just the fundamental geometric limitations. And so the sort of like independent dependent variable analysis that they did is if we fix d, which is the vector embedding dimension, and we fix k, they just set k equals 2 here just for computational reasons. This doesn't matter that much as long as k is fixed. So fix k at 2. And then we slowly increase the number of documents we have, sort of like the complexity and amount of like sort of nuance in the vector embeddings we need. Like start with like, I think n equals 1, and then just go up until this fails, meaning that there is a query whose k most relevant documents by cosine similarity is not the subset of size k that we designated it. And so like, I guess if you look at this graph here for d equals 20, they were able to get all the way up to like n equals like, I guess it's like 150 or whatever. Before we had a failure. And they did this for d from like 2 to like 45. And they fit this polynomial against it. So this is like the first n where it fails. And basically what this result is telling us is like, if n is like essentially like cubic in d, then we start having representation issues in terms of these size case subsets. And I guess like a more like interpretation of this is like the first value in parentheses is D, and then the value outside parentheses is N. So like if you have a dimension of 512, which is like pretty common, when N is around 500,000, then you start having these sort of failures. Yeah, I think all these other dimensions are like pretty common in base embedding models. And although like these numbers might seem large, 250 million, 107 million, there are like real world applications of retrieval where you just have massive that exceed these values, and you just start having like actual uh, retrieval failure. So this is sort of like validating the like mathematical results that were stated earlier with this sort of like very idealized experiment. And it shows that like, yes, if we have a corpus of documents that is too large, even with all these ideal constraints, like we're not even worried about like having batches that are too large, like for compute reasons or whatever. You just get failure a polynomial scale. I guess I'll pause real quick and see if there's any questions.
The question is the limit in terms of n depending on chunks or number of documents?
Yeah. So if we're talking about this sort of experiment in particular, the limit is solely based on n. So like this whole like y equals like this cubic in D. This is just a bound on when n, or the number of documents you have, when it gets sufficiently large, we start having representation failures. In terms of chunking, this sort of bound doesn't consider like different ways of chunking. Chunking is like, actually, let me step back on that. We just start with like a base embedding model, and like the whole training process is like altering the how you embed vectors. And so like they do this with like normal backprop, whatever. But so to answer your question, no, like chunking is not the like thing that they're altering or like playing around with to see like when n will start failing. I remember I looked at the GitHub. I think they tried this for multiple different base embedding models and multiple different ways of like chunking, which or not like altering the chunking for each base model, but because every single base model is a different way to chunk. And like this is not what they're altering basically to like find when the corpus is sufficiently large where we have retrieval failures.
It seems like it's based on the information that you're trying to encode and an embedding, which can be a chunk, can be an entire document. So it's whatever type of information that you're trying to encode, and yeah, that can be anything. In this case, I think it's like just short chunks, but it really depends what you're trying to embed as the ground truth, as the information that you're trying to search across.
Okay, so we have another question. If we know that the dimension D is too small, what is their bound on what D needs to be so that it's large enough? So I guess if we're still speaking about this experiment, like I guess like the approach is like in theory you could just have we have a upper bound on n essentially, where if n is too big, then we have a failure, right? So an upper bound on n would correspond to a lower bound on D, right? Like I think we can just take the like sort of inverse of this cubic, like obviously on like a sufficient domain, right? And if we flip it, then we have a lower bound on D in terms of n. Does that make sense? Yes. So if we have like we know n, which is like the number of documents, right? I guess at least in this case where we have like the n choose k queries, we have like this sort of setup where we want to just like this is like this set of like queries that we're aiming for. It looks like empirically that we can just like sort of invert this function and get a lower bound on D, where getting like all of the correct top k's is like even something we can hope for in this case. The authors don't really produce this sort of graph for like more arbitrary sets of queries. But I think like as an extension to this paper, like we or someone wanted to do that, this would be interesting. And we could just like flip the order of like the variables. We get like D in terms of n versus n in terms of D. So we have like a critical D instead of a critical n. And then like also have less rigid constraints on the like number of queries and what we're hoping to like sort of see as a ground truth out of queries. But yeah, that'd be interesting. Okay, next question. Does this paper help us to find an optimal dimension size for a given chunk size? No, this paper does not really cover chunking at all as like a thing to alter or play around with. But yeah, I mean, I think it's another thing to think about. And it might be especially relevant after the next section because like they have very specific types of queries and documents where chunking could influence the results. Does this limit curve assume a certain cosine similarity value required? No. So cosine similarity is obviously normalized to -1, 1, right? We're thinking back sort of to the threshold idea. So what this experiment is looking at is like if we have this n and like D and N choose K, if we run training and just like sort of optimize how the vector is replaced in space, is it possible that for every query, K, size K subset that it corresponds to, all of these cosine similarities high or like higher than all of the other ones? So no, we're not looking for perfect 0-1 correspondence or 0-1 like split. What we want is like after this sort of like optimization and training, for every single query, the size K subset that it corresponds to, its cosine similarities with all these documents are high. So let's just say like 0.9, 0.85, 0.8. And then we want all this to be like higher than a certain point. Let's just say like 0.7. And then we want the cosine similarities with every other low document to be like 0.3, 0.4, like 0.5. As long as there's a way to like split these two into a higher region of relevant documents, or these K documents in a lower region of N minus K, we're happy, because like this means like there is like literally like a practical way to like split relevance and irrelevance. This is just sort of the model of like how cosine similarity tells us relevance within like this paper. And it generally is just like a very common like paradigm for like how you have a threshold for determining relevance versus irrelevance. So no, you do not need a perfect similarity of 1 for this limit curve as an assumption. I think I'll keep going, but if there's questions, yeah, we can come back. And so now we get to the part where the authors actually construct the like limit data set, and it's like sort of like what the paper is known for, right? Like it's called the limit paper. And so because we're interested in just looking at the fundamental representational limits of retrieval, the author's goal is not to create a data set with super complicated queries. So sort of like this like literature overview, they talk about like a lot of different data sets where they are notable and difficult because the queries have like sort of like complicated like logical operators. So like an example query would be like find all like documents that have X or Y or like Z, A and B. So like they're just using or operators in natural language to basically like create queries that are complicated enough that they could reasonably like trick current state-of-the-art embedding models and sort of just like prod their limits in this fashion. And so these are like important data sets. They're good for testing like embedding models on queries like that, like, let's just say like a scientist or like someone would use where they need to have very precise limitations or objectives of what the prompt or query is looking for. However, because our goal is to see like, let's strip down all of these other limitations and see like, can we even just have a mathematical embedding where like we can get certain relevance patterns? The queries and documents that they use for their limit data set are much simpler. And so I'm going to pull up the GitHub for this paper here, and so we can just on a high level what they look like. And so first we'll look at the documents, which are the corpus. At the start of this sort of setup, we have like a list of attributes, like people attributes. Here we have like things that people would like, so like cinnamon rolls, in like this second row, cherries. The next row, like this person like likes mechanics, so they probably like cars, eyeglasses. Sort of just like very generic attributes that a person can have. So this is just like the start of the experiment. Now, we have a fixed number of people, in this case like 46, and for each of them, you give them the same number of attributes. I think it's like 40 something. But everybody you have a list of attributes that have been pre-vetted, prevent like interference or whatever. And then for each person, we randomly sample like I think 45 attributes. And then the document associated with that person, we have Geneva here. The document is really just like Geneva likes A, B, C, D, like E, F, all the way down to like all these attributes. And so these are like pretty simple documents relative to most data sets. And then the queries are also just, we select a single attribute for each query from this sort of pre-existing list of attributes. And we ask as a query, literally like word for word, who likes X, who likes Y, who likes slide rules, who likes disco music. And so these queries are very, very like simple. Like they're basically like bare bone translations of like logical like questions like who has like X or like is X an element of this document, but you obviously translate it to natural language because like this is what actual like state-of-the-art embedding models are built off to intake and output. And so yeah, like they have a sort of methodology of like how they set the hyperparameters, but what we need to know is like there's the 46 documents or 46 peoples with list of attributes, and then our queries are just single attribute asks who likes X, who likes Y. And so the setup is convenient because it's very easy to sort of have a ground truth for relevance. So like the ground truth for who likes apples is you literally just do like a keyword match through every single document of like which document has apples, and that's sort of your ground truth relevance set. But obviously, like we're gonna run these through a like existing embedding model, and then use the cosine similarities to see whether these sort of ground truth relevant documents are what is returned. And sort of to be more concrete with this, we have our 46 documents, and then we have our set of queries, like who likes X. And ideally, you'd like to see the documents that actually contain the word X, like apple, to be at the top of the cosine similarity. And so one metric we can use to measure this is called recall at K. And so probably should write this out, but recall at K is how this is written, is equal to the proportion of relevant documents by keyword matching, in this case, appear in the top K docs by cosine similarity. So to clarify, recall at K, just like we're looking at a single query right now. You look at all the documents, you do cosine similarity, and then you rank them from like highest to lowest. And we look at the top K of these, and we see how many, rather, you look at the top K, and then you see how many relevant documents there are in these K. And this is our numerator, and our denominator is just the total number of relevant documents. In this case, the number of documents that keyword match with the attribute that we're querying for. And so like, I guess, so picture if we have relevant documents that are drawn green, like then our K is like 5, and we have like irrelevant red documents. Like the recall here is like 3 out of 5. So like the recall is like 0.6 for this query. But in practice, you just do this for all queries, and then you average the values to get like a global recall at K for a given test set and model. And so ideally, you want recall at K to be high because we want the relevant documents to show up early in the ranking of cosine similarities. This is the mark of a good embedding model, or one mark of a good embedding model. But what they've shown is that like literally with the simplest queries possible, who likes X, and very simple documents of like listless attributes, the recalls at K are terrible for all of these state-of-the-art embedding models. Recall at 2 is like literally just squashed at 0 for all of these like embedding models. Even recall at 100, actually I should go to this graph instead. Recall at 2 is like not very good. You can see like the scores are maximally like 0.5 for the best model, with a high number of dimensions in 4096. And even recall at 20 is like not perfect. And this is like very bad because if you think like to our hyperparameters, there's 46 documents and we're taking the top 20, which is almost half of them. And if we can't even have all of the relevant documents by keyword for a query in the top 20, this means the embedding model really cannot represent information in a way that sort of surfaces these documents based on the query. Sort of again, the idea is like stripping down the queries and documents so that demystifying language or like logical tricks we could have, and just seeing like, oh, can these supposedly really good embedding models even embed these queries and documents in a way we have relevant documents surface as measured by this like recall metric. And so this is just like further evidence that embedding models are limited in the scope. And yeah, I think this is like sort of the main point of this section and this sort of data set construction and experiment. There's like other small modifications and like other points of analysis they do, but I think they're not very important to look at right now. And I guess I can pause for questions real quick.
I have an animation in one dimension that I'm sharing. Do you see it in the chat? Maybe you want to click on that just to show.
Yeah, I can. Yeah,
It's the intuition in one dimension.
Yeah.
Where if you're trying to embed these 4 vectors along just one line, with top K equals 2, there are certain configurations that you will never be able to retrieve. For example, who likes flowers? So retrieving the blue and the red is not going to be possible.
Yeah, so I think one dimension, there's like only one notion of ordering, literally just like the order on the number line. And like the first and third like documents / people from the left are the ones that correspond to flowers, right? Like V1 and V3. But if we have top K, if we want K equals 2 as our top K, then we like literally just don't have enough space to like move stuff around to where like we can get those as the top 2 like documents or people. Yeah, so this is a sort of simple picture, but for like even for dimensions that like exist outside of our world are like 100 or 100 dimensions, there's still like you just run out of space when you have like enough queries and documents where like we can't get all the patterns we want. So like this is just another way to validate this sort of like theoretical result. If there's no other questions for now, I think I'll sort of recap the main points